Welcome to today's lecture. During the past few weeks, we had a glimpse of the wide spectrum of ore deposit types that occur in various parts of the world in different continents. We have just had a glimpse of them, and that was the initial part of the lecture series that we intended to cover, with intending to obtain a overview, brief idea about the geology, about the principles of ore deposit formation, and what we have learned so far can be called as just the alphabets of the subject of ore geology, which has a lot of intricacies, and many of the ideas that were originally proposed on the deposits are constantly getting refined with availability of modern techniques, microanalytical techniques, new ideas emanating from using many different techniques like the rare earth elements, the stable and radiogenic isotopes, ideas about the sulfur isotopic makeup arising out of inorganic and organic reduction of the seawater sulphate, many experiments conducted on many systems to quantitatively understand the processes of fractionation of different metals in different systems, and many of the deposits, many of the well known deposit types have witnessed a lot of debate as far as their origin is concerned. For example, the paleoplacer deposit at Witwatersrand Basin in South Africa, which was for quite some time was held to be a deposit which originated from the mechanical concentration type process, was very strongly debated for its origin from a hydrothermal fluid, which was almost akin to the hydrothermal system that give rise to the lode type gold deposits. But later on again many detailed study have revived the concept, they revived the idea about the origin of such deposits. Similarly, there are many such instances, and we have not so those are the things which you will all be learning in your advanced level courses on ore geology. And we have seen that this wide spectrum of ore deposits occurred throughout the geological history, starting from the early Archean till the Quaternary, and many of the deposit forming processes seem to have been very restricted to certain time period. For example, the banded iron formations, which never, the process was never repeated in the later part of the geological history after the late Proterozoic. Similar is the situation with the paleoplacer deposit of uranium, and some deposits like the porphyry copper deposits are not found to be occurring in any of the older cratonic blocks, and understood to have been forming because due to, in the process of the plate tectonic type process, which is operational at this point of time from the present day global tectonic setup. So now, with this brief background, it would be good to see as a component of this course, and which is usually required by students in the Indian context, to have some idea about the deposits that are occurring in the Indian subcontinent, more specifically in the peninsular Indian region. And this discussion is cannot be very exhaustive, because the deposit types are so many, so vast, and occurring in different parts of the peninsular India. It is not possible to give a very detailed account of all such deposits that occur in the peninsular India. So, we will all be restricting ourselves to some very selected deposit types, and most of the discussion will not be based on statistics. For example, the quantity of the metal available in such deposits and such kind of parameters, which can be obtained from many available resources. For example, the Indian Bureau of Mines or the information from the respective mining companies. So, I will not be getting into much of the details about the quantity quality aspect of these deposits, and will only be discussing such deposits with an idea as to the potentials of different parts of the peninsular India, and the what could possibly look like as the future scenario. And because in the beginning, when we were discussing about the mineral deposits in the context of the Indian economy, we stated that the role of mineral resources in the growth of the Indian economy is not that very distinct, although as a country we still depend heavily on our mineral resources for the growth of our industry, falling short on many of the critical and strategic minerals and metals. So, with this we will just have a brief overview of the Indian scenario, where so as you could see here, this is a almost like a country scale map, geological map of India, and here we could see that this peninsular India is most part, which is basically covered by the Deccan Traps shown on green here. This is the part Deccan Trap which covers a substantial part of the peninsular India, and just keeping that aside, we see that this Indian peninsular India is basically an amalgamation of a few cratonic blocks, old cratonic blocks, Precambrian cratonic blocks. Those are the this is the Dharwar Craton, and below is the southern granulite belt. This is the Dharwar Craton here. This is the Bastar Craton. This is the Bastar Craton, this is the Singhbhum Craton, and this is the Aravalli Craton, and this is the Bundelkhand Craton. So, these five main cratonic blocks constitute the Indian subcontinent, and as we saw before, so the total area that is covered by rocks of Precambrian age are quite substantial, and we could expect that the mineral resources also would be coming from dominantly from these broad areas. Let us first get into let us first see the mineral potential of this Dharwar Craton, which will be again getting into looking at a little larger scale map. So, this Dharwar Craton is the cratonic block which represents. So, the Dharwar Craton is essentially divided into the eastern and the western Dharwar Craton, and the and the close bed granite, which is occupying the median region of the craton, and along with some crustal scale structural feature like this Chitradurga shear zone over here, it is divided into the eastern and the western Tharwar craton. Now, what is shown here in this purple color bodies, these are the schist belts of the western and the eastern Tharwar craton, and this eastern Tharwar craton and the western Tharwar craton are quite endowed with resources of gold. In fact, most of the production of gold at the present time in the Indian context comes from the eastern Tharwar craton, with some new deposits also coming up from the western Tharwar craton from the Chitradurga schist belt, which I will be just showing in a larger scale map. Since this Tharwar craton, these schist belts essentially are the metamorphosed greenstone sequences, which are the volcanosedimentary rift related volcanosedimentary sequences of Archean age, which are metamorphosed and are exposed in the form of schist belts consisting mostly of amphibolites and sometimes lower grade chloritic rocks, and this cratonic block is traversed by parallelly disposed a number of shear zones, and those shear zones have been the locales in which the major and the rich gold mineralization have taken place. Since these are the old greenstone belt, as we have seen in many of the cases, they are also potentially rich in the algoma type iron formation, which comes from this, the Archean sediment hosted manganese deposits, volcanogenic massive sulphide deposit like the one which is reported from Ingaldal area in Karnataka. So, this Tharwar craton, which spans the area of Karnataka and Andhra Pradesh, many of the prominent gold localities come from these two states. The one of the major gold locality which produced the maximum amount of gold and has the history of gold production of more than 1.5 centuries, but got closed just about a decade back, is the famous Kolar gold deposit, currently producing gold mines mostly in the Hattimaski schist belt, and new deposits being discovered in the Gadag schist belt. And also, as we saw before in the greenstones, there the ultramafic bodies, which we see the metamorphosed ultramafic bodies of the earliest volcanic activity, we also do get some amount of chromium. So, this Tharwar craton has actually can be visualized as a huge metallogenic province, giving a substantial amount of production of iron, some amount of manganese, major gold deposits in the country. So, coming to the Bastar craton here, one thing we can is very obvious from the this very small scale geological map of India, is that in almost all the cratonic blocks that we see, we get extensive granitic activity which mostly dates between the late Archean to early Proterozoic kind of period, and which coincides with a major crust forming major growth is very steep and a very fast rate of growth of continents during that time. So, these prolific granitic activities also had a lot of metallogenic implications, and in addition to that, almost these cratonic blocks, they are essentially constituted of the basement gneissic complex. In the Tharwar craton, they are known as the peninsular gneiss. In Aravalli craton, they are known as the bended gneissic complex, and in the Singhbhum craton also they are similarly named, older metamorphic gneisses, and so on. And in Bastar craton also we do get the basement gneiss. So, Bastar craton is also a very interesting geological situation, although there is no such prolific development of such greenstone belts, but some very rudimentary greenstone belts have been reported from here, where sporadic occurrences of gold has been reported, but the major mineral potentials of this Bastar Craton is the copper deposit coming associated with granitoid here, and also some amount of tin associated with granite pegmatite, which will be seeing them in little details, and the adjoining this Bastar Craton adjoining saucer metamorphic belt is the major manganese producing region of the country, and coming to the Singhbum Craton. So, these cratonic blocks are also bordered by the mobile belts, and here this is the Eastern Ghats mobile belt, and also this the Singhbum Craton in, and also the Bastar Craton has been the two major important sources of iron deposits, which belong to the superior type of iron formation in the Singhbum Craton here, and also associated with the Archean with the same time period the manganese deposits, and as we shall see a little bit in a larger scale map, the Singhbum Craton also hosts one of the major metallotect in the form of the Singhbum shear zone, which gives which has produced substantial amount of copper, and in addition to that is also one of the uranium rich areas of the country. And as far as the Aravali Craton has been the major contributor of the lead zinc deposit in the form of the sediment hosted massive sulphide deposits or SMS or the SEDEX type of deposit, coming mainly from the Aravali fold belt in the Rajpura Dariba, in Jawar, and in Rampura Agucha, which will be seeing them a little detail, and also the North Delhi fold belt, where a major copper producing zone has produced quite substantial amount of copper, and in addition to that there are many other mineral commodities which are produced from this particular craton. We will be seeing them only selectively, and this is the Bundelkhand Craton. Bundelkhand Craton is and also in between we do have some very rudimentary or very not so well developed greenstone belts coming from the Mahakoshal belt over here, and which also have been reported to be gold bearing in some certain restricted areas, and similarly also from the Singhbum Craton there are some such occurrences which have been reported. So, if we look at the mineral potentials of the Indian peninsula or Indian subcontinent as a whole, we see the statistics a little bit over here. That is about 3.28 million square kilometer. The hard rock is about 2.42 million square kilometer if we exclude the substantial area that is covered by the Deccan Traps. The alluvial cover is about 0.6 million square kilometer, and on the right the information that we have is that we are the dominant producer of the industrial mineral, which is mica, mostly coming from the mica bearing pegmatite belts in Hazaribagh district in Bihar. Barite, we are second in production of barite, we are third in producing chromite, which is basically coming from the Singhbum Craton, a little bit from the Dharwar Craton also along with the old mafic units, and the major chromite resources come from the Singhbum Craton, which we will just have a look when we see the Singhbum Craton map in details. And since we are not covering much of the non-metals and the hydrocarbon resources, still as a piece of information we are also fifth in producing coal and lignite, and we are sixth in iron ore production, and bauxite and manganese we are sixth and seventh respectively. Okay. It would be good to see, or it would be worthwhile to make a correspondence with the different genetic deposit types that we just went through. And if we go by commodity wise, then first consider the most abundant of the metals as iron. So, the iron are sedimentary and the magmatic affiliation. As you have seen the genetic types, the sedimentary chemogenic sedimentary deposits are the banded iron formation, the ironstones, and the magmatic type are the Kiruna type and the layered complexes. The ones which are marked in white boxes, generally that such type of deposits we are not considering here, and also the ironstones are not considered as resources of iron, which is considered for some separate resources. Coming to the banded iron formation, we have the Algoma type, superior type, and Rapitan type, and we do not have any report of occurrence of any Rapitan type banded iron formation in anywhere in the peninsular India as of now. So, we do have the Algoma type, which I have just mentioned, occurring in Dharwar Craton in the Kudermukh area, and the some other part in the schist belts of Dharwar Craton. Their affiliation may be a little bit uncertain, could be superior type associated with volcanic members, and the Singhbhum and the Bastar Craton, which are definitively of the superior type, although there are some references of them being greenstones, but the widely held idea is that these deposits which are occurring in the Singhbhum and the Bastar Craton, like the iron ore craton and the Bailadila formation in central India in the Bastar Craton, are the superior type iron formations occurring in extensive areas of hundreds of square kilometers. So, we will go to that, but magmatic affiliation generally we see as layered complexes, what we have seen in case of Bushveld complex occurring, or the layered complexes occurring as oxide layers with the intermediate type composition, anorthositic aproic type of composition. The only occurrence that we have in the Singhbhum Craton is the Simlipal complex, which comes to near to that. There are certain uneconomic occurrences of titanium and vanadium bearing iron oxides associated with the Simlipal complex, the details of which we will not be discussing here. Okay. It is a map, it is a little larger scale map of the Singhbhum Craton. This is the Singhbhum, this is the Singhbhum mobile belt separating the northern, the southern Singhbhum Craton. I would like to draw your attention to this particular the western part of the Singhbhum Craton, which is essentially known as the Noamundi basin, and which hosts the rich iron deposits and producing the iron ore in good quantity for our domestic consumption as well as for exporting. And in this craton we have this Noamundi basin and the Gorumeshani Badam Pahad basin, which is also another iron ore basin in the Singhbhum Craton, and the Daitari basin, which is very close to the Sukinda thrust, which is on the southern, which marks the southern boundary of the Singhbhum Craton. And if we look at a little bit of a larger scale map of this Noamundi basin, which is essentially in the form of a, which is popularly known as the horseshoe synclinorium, essentially a synclinal structure, and the iron formations are shown with this black thick black curves and the patches here. So, those are the different locations of the rich iron occurrences, although this belt runs for a few tens of kilometers here. The iron deposits are localized areas, the enrichment has taken in different smaller localities. What is suggested is that this particular synclinorium, the eastern limb, the ore deposits are more on the basinal, because after the major phase of deformation which has given rise to this synclinorium structure, there has been a cross folding in an east west fold axis and has given rise to this complicated structure. And as it looks like, the localization of the enriched iron ore in this particular region is very much structurally controlled, where in the eastern limb the major ore localities, the mines, are essentially based on the domes that is formed by the cross folding, and on the eastern limb it is on the basins. And also, as we discussed about the very close geochemical affinity and the spatial closeness of occurrence of iron and manganese, that we could see it clearly from here. This is the core of the synclinorium, which hosts a number of important manganese localities as is shown here. And what exactly we have when we see these iron ore deposits, and we go by the principles and the origin that we have discussed about the iron formations. Extensive iron deposition from the sea water, which was very rich in its iron held in +2 state, and the conditions were favorable with the increasing atmospheric oxygen. They gave rise to the iron ore formations, which originally were deposited as the laminated or the iron ores with mesobends of iron rich and silica rich layer, but those could not be directly used as iron ores, because the iron content will hardly go to 17-18%, whereas the ore which can be treated for extraction of the metal would require to at least 55% of iron. And so this is understandable that these deposits must have undergone some enrichment processes after the formation, after their original deposition. Here is an example of what exactly we get in an iron ore body, which is taken from the Noamunde basin. It is a hypothetical reconstruction from the drill hole data by Buick et al. Very recently, where we see that in fact when it occurs as a mineable or mineable ore, there they occur in much more enriched form as ochre or as lateritic ore, as goethitic ore, where it is mostly iron, as soft hematitic ore or flaky hematitic ore, blue dust, which essentially are the products of processes of enrichment. And that is the reason why it has been suggested that such basins, after as we see them today in their deformed state and also have undergone variable degrees of metamorphism with reconstitution of the layers and essentially selective leaching of silica because of hydrothermal solution, and those hydrothermal activities could be much later than the formation of these iron ore basins. And even the enrichment process, which we also discussed during our discussion on the residual concentration process, we also saw that rich iron ore deposits also occur or can come into existence after they are subjected to such kind of enrichment process, which could be even very late in the geologic history, almost in the Cenozoic time. So this exemplifies, and such kind of whether it is the iron ore basin in the iron ore craton or in the Bailadila basin in central India, the story is the same, that the originally deposited formations of in the form of banded iron formation with the mesobands of iron rich and silica rich layers. These materials have to undergo enrichment through process of hydrothermal activity, and further enrichment process even almost like surface operating meteoric water, because due to prevalence of conducive environment, the iron ore gets further enriched to give rich ore bodies. Okay, so we will continue our discussion of the Indian ore deposits in the next class. Thank you.